Welcome to Lecture 7.3, the transport equation. Let's motivate where we're going with this lecture. So we've seen the heat equation, which is this thing right here. In this lecture, we will introduce the transport equation, and this will allow us to derive the wave equation, which is almost the same as the heat equation, but it just has an extra t in it right here. Okay, so let's do an example. Consider the following PDE involving a function u of x and t. So I'm going to write this two different ways. I'm going to rewrite this as ut minus c times ux equals 0. Agreed? But I'm also going to write it, just get used to something, on the left, ddt minus c times d dx times u equals 0. So what is this thing here? This is a differential operator. And you can add these things together, you can subtract them, you can multiply by constants. This thing attached to a function u, I'm going to write it up here, so d dt minus c d du. So think of this as like something that I can attach onto u, and if I do that, I get the u sticks on. So du dt minus c times du, oh sorry, this here should be, next one here should be an x, du times dx. Okay? If you're like me, you probably took calculus, and you always wondered why the second derivative is written d squared y dx squared, right? I said, why the heck is there a 2 after this and before, in between that? Why? And the reason is because the second derivative applied to y. So let's take y and let's apply dx to it. So this is an operator applied to y. An operator is just a function of functions. So this is a function of y. And now let's apply derivative again to it. So let's dx of that. So what happens when you concatenate all these things together? You do get, there's dx times dx on the bottom. There's my dx squared. And at the top you get d times d squared y. So that's where this comes from. Okay, that was a little bit of a tangent, but let's continue now. So we want to solve this PDE. And I'm not going to find all solutions, but I'm going to give you a family of solutions or a family of functions that is a solution. And I actually don't know what all solutions of this look like. I would assume that what I'm going to show you is all of them, but I'm not positive. Okay, so I'm going to let, let's get my, pen back. I'm going to let f of x be any, to be safe, let's say differentiable, one variable function. And I'm going to define a two-variable function using f. So I'm going to define u of xt to be f of x plus ct. Let's take a moment to think about what that is. One way to plot that down here is, let's suppose u is, or f is this function. Well, I guess I said it would be differentiable. Let's take a little bit of sandpaper and smooth this off so it's a nice smooth function. And then what is, so this is a function of x. So f of x plus ct, what does that look like? Well, let's not plot this in 3D, but let's plot this in 2D where t is time. If this is ct, then that function is well, I'm trying to draw this just as a shifted copy of it. I don't know if let's try that again. And again, we take our little sandpaper, smooth that off so it's differentiable. Although I think we can probably get away with this being piecewise differentiable. Anyways, this this is u of x0, and this function is u of xt, which is f of x plus ct. So this thing here is a traveling wave left, oops, L-E-F-T, left at speed c. And I claim that for any function f, this thing satisfies this equation. And that's why it's called the transport equation to the left, because it transports this function to the left at speed c. So this thing here is going to the left at speed c. Okay, so let's check the chain rule is needed to take the partial derivatives of this. So what's what's ut? What's the t derivative of this? So that's ut is f of x plus ct times dt of the inside, x plus ct. Remember that? Single variable calculus. So that is just c times f of x plus ct. And then ux is, oh, I forgot my prime here. F prime of that. Ux is f prime of x plus ct times the derivative, the x derivative of this, which is just 1. Okay? So let's note now that I claim this u solves this PDE. So ut minus c times ux equals c times f of x plus ct minus c times f prime. I forgot my prime up there as well. Sorry about that. F prime of x plus ct equals 0. So we have found a family of solutions for any one variable differentiable function. If we make it into a traveling wave left, then that function satisfies or solves this PDE. Okay, so example 2 will be very similar. The only difference is that we have a plus here instead of a minus. So I'm also going to write this two ways as ut plus cux equals 0, but also as dt plus c times d dx, this operator applied to u equals 0. And I should say that, just again as another tangent because I can, the reason why we call these differential equations linear that have like t squared in them is because they can be written using linear operators. This is a linear operator because this applied to u1 plus u2 is this of u1 plus plus this of u2. So for example, just again as an aside, y double prime plus t squared y equals 0. This can be written as d squared d squared, oh yeah, that's right, d squared dt squared plus t squared times, yeah, that is an operator, a differential operator. And if I attach that, apply it to y, and say what functions are killed by this operator, that's the same thing as saying what functions solve this differential equation. So this is a linear operator, and that's what we call this a linear differential equation. If I had a y squared in here, then we couldn't do something like this. And that's why there's such a beautiful theory about linear differential equations, is because you can write it like this, and then you can turn it, and then you can use high-powered tools from linear algebra to answer these questions. Okay, so end of this tangent, back to here. This equation, let's solve this. So I'm going to let g of x be any one variable, and I should probably say differentiable function. And I'm going to define u, as before, I'm going to define a two-variable function to be g of x minus ct. So let's sketch what this looks like. So if g now is some function like this, then this is u at time equals 0, which is g of t, sorry, g of x, not g of t. Then this function is u of xt, which is g of x minus ct. So this is a traveling wave to the right at speed c. So this thing here, let me write that as a traveling wave right at speed c. So I claim that this solves this PDE. So let's check by the chain rule. Ut is, well, let's write it out, ut of xt. That's just the derivative of g, x minus ct, times d dt of the inside, x minus ct. So that's minus c times g prime of x minus ct. And then u x of xt equals similar, it's the derivative of this times, well, times the derivative, the x derivative of this is 1, so that's just that. Okay, so note that this function solves the PDE because if you take ut plus c times ux, that's taking this plus c times this, you get 0. So note that ut plus c times u x is negative c g prime of x minus ct plus c times g prime of x minus ct, and that equals 0. So indeed, this is a PDE. We call it the transport equation. To the right transport equation, this is a solution, and solutions look like waves or functions that are transported to the right at a constant speed c. Okay, so let's put together what we've learned in the previous two slides. So here's a PDE. I'm going to box it. And if you prefer, I'm going to write this as UTT plus, not plus, minus c squared UXX equals 0. Now another way to write that is like this here. And it's not clear how I'm going from here to here, but bear with me. So this thing here, you can multiply these operators like you do functions and think of them, think of this as a difference of squares. So this is like d squared dt squared minus c squared d squared dx squared applied to u. So this times u is this thing applied to u, which is just this thing here. So I can write it like this. Okay, so now I'm going to let f of x and g of x be any one variable let's say differentiable again functions, and I'm going to define u of xt to be, now what do I want to say? How about f of x plus ct plus, make sure that looks like a t, plus g of x minus ct. Okay, so this thing on the left is, this is this transport to the right, the operator, and this thing, we gave us the PDE, that was transport left. And I forgot my t over here. Okay, so this function applied, if I plug it into this PDE, or this PDE, then I hit it with this operator and then this operator. It doesn't matter what order, these things commute. And then I'm asking, does this thing go to 0? Well, let's see. The F part, this thing is going to be killed by the transport left operator, and this thing is going to get killed by the transport right operator. So this thing I claim is a solution to this PDE right up here. So it's easy to check that u of xt is a solution to, put a star there, that PDE. Okay, so now I'm going to write an initial value problem. So consider the following initial value problem. So here's UTT equals c squared uxx. So this is the wave equation. It's, I guess I haven't called it the wave equation, but it's this PDE up here. And then let me give an initial condition. U of x0 equals f of x. So just a function. It doesn't have to be this function, but why not? And then let's say that u t of x0 equals 0. So this thing here is so we're going to call this the wave equation. That's the name we're going to give this PDE. This thing here is just the initial displacement. So it's an initial, both of these are initial conditions. This is initial displacement. So it's like the initial wave. And this thing here is the initial velocity. Now it's not the initial velocity as the wave left or right, it's for every point, it's the initial velocity up and down. So is the wave traveling up or is it traveling down? So this is an initial value problem. And a picture of this is, let's draw this down here. How do I want to draw this? Let's do this. So here is the initial, say that this is f of x, right here, and this is x. So I claim that a solution to this initial value problem is, think about it. Well, before I say it, let's try to figure out intuitively what it is. Let's suppose that this is a big wave in the ocean, or displacement. Or maybe this is a string and you pull it tight. Yeah, this is better. A wire and you pull it up like this, so there's an initial wave, and you let go. Initial velocity is 0, so you let go. What's going to happen? Well, half the wave is going to travel this way, half the wave is going to travel that way, right? The energy is going to dissipate. So what's going to happen is at time ct, or at time c, I should say, at time t, claim that this is going to be what happens. Is we're going to get half of the wave going that way and the other half of the wave going this way. And this function here on the right, this is going to be 1/2 times f of x minus ct. This function on the left is going to be 1/2 of f of x plus ct. So this is traveling that way and this is traveling that way, both of them at speed c. So in other words, I claim that the solution to this initial value problem is u, oops, that's not a u, is u of xt 1/2 f of x plus ct plus 1/2 f of x minus ct. And I will let you check that on the homework or a worksheet. I'm not going to do all the details, but I think you should just see, I know that it's just an exercise involving the chain rule, nothing complicated. And hopefully it should match our intuition, that the solution at any time t, we have half of the initial wave out here and half of the initial wave out here traveling to the right at speed c. So to summarize, if we have a two-variable function of position and time, then the heat equation is this PdE and the wave equation is this PdE. So in this lecture, we just saw waves on this infinite string. You can think of this maybe as like the ocean that goes on for a long time, or an infinite string. And so what we got is, we're looking at waves that were going maybe in that direction and waves that were going in that direction. But what we want to do in the next lecture, and I'm just going to give a preview here, I'm not going to actually do much of it, but we want to measure waves in a finite string. So it's like plucking a guitar. So a string of length L, maybe we have an initial wave like this and we want to pluck it and it's going to vibrate back and forth. But as you know, if this is not just a sine wave, this might be some triangle wave or square wave, it's going to be made up of a bunch of smaller waves at different frequencies. So waves that might vibrate in the string look like this. So we are going to want to impose boundary conditions. So boundary conditions and initial conditions. And for example, what we'll get is we'll get a PdE that looks like this. We'll get some boundary conditions where the endpoints are going to be fixed at all time t. So that means that u of 0 t and u at 0 at L of t are 0, and then we need not one initial condition but two, because we have two time derivatives. It's like when we throw a ball off a roof and we have an equation for that, we need to know the initial position and the initial velocity. So the initial position is u of x0 equals some function h0 of x. This is the initial displacement. I should probably say that u is, in this case, is displacement. Let me write that up here. U of xt is displacement at position x and time t. So for example, if this is x0 right here, then this right here is u of x0, forgot my x0, and t. So if we just look at this little particle, this is going to, as time goes on, it's going to be bouncing back and forth like this. So not only do we need initial displacement, we also need the initial velocity. And this is, again, velocity of this little particle. Is it initially going upwards? Are we pushing the wave upwards? Are we throwing it downwards? Or are we just letting it go? So this is the initial velocity. Okay, so we will, next time we will formulate this for a specific example, and we will solve it and compare our solution to that of the heat equation.